He's the author of multiple books and also articles, and today he's going to teach us how to make good graphics, how to avoid bad graphics, and how to identify the difference between the two. Please welcome Dr. Strauss.
Okay, thank you very much to the organizers, to the PhUSE conference. I have to say I was quite impressed, quite amazed by the professionalism of the organization. They asked me for the slides like 4 weeks up front. They actually dared commenting on my slides and asking questions. So it was pretty professional. Thank you very much to Joseph and Kamer for this. Right, so I'm going to talk about graphics of clinical data. We're going to bridge now the general principles we got to hear about a little bit in the beginning to applications to clinical data. And I'm going to talk about particular examples, inspiring examples, something we can learn from, that is good graphics, bad graphics, and also ugly graphics. We will see each of those later on. So first slide is a combination of the two most important events that take place these days in the world. The one is the World Cup, and the other one is the PhUSE Conference on Visualization, obviously. And at the intersection lies FC Basel. So we're going to look at, that's actually the way to put the Swiss back into the cup, but okay. So we're going to look at how you order a ticket for FC Basel. And it's actually quite neat. If you click on I want a ticket on the home page, you get shown a map of the stadium. You see the field in the middle. You see the stadium all around. You can use the mouse and hover over the different blocks. And it shows you this is sector A5, A6. It's got 96 seats available. The price per seat is 75 and the like. So that's quite neat. And you can decide where you want to stand or sit. You select a particular category. In this case, you select block A2 down here. And up pops a map of the block and the individual seats. Right? So if you're quick, you can select your seats because you notice, aha, there's seats available in the front row, so why not sit in the front row? You select the ones. And only if you carefully investigate what the graph tells you, you would see down here it says Spielfeld. This is where the field is now. Now the field is at the bottom, right? And if you're quick and click on the front row, you'll be sitting in the last row. Right? So you better watch this carefully, what you're doing here. And that's actually dangerous. The first message here is do not rotate the axis. Do not mess about with the orientation of the graphs, but keep them consistent. It's pretty bad, but that's not the end of it, actually. When I wanted to select some seats further up front, and I thought, aha, there's still some stuff available, and I couldn't select the seats. I thought, maybe a browser problem. Started up another browser. Also didn't work until it hit me. And the solution is the seats that you can still get are the red ones. All right. It doesn't make any sense. It's against any kind of intuition, because color carries a connotation. There's an intuition behind it for the human beings. So that means do not mess about with the orientation, the axis and the like, and use an intuitive color scheme if you use any. But that's a pretty bad example. So the animation is very fancy, but the intuition doesn't work here. Haven't spoken to Basel FC yet. Here's another example for what you can do to influence the visual perception of your graph. That's actually quite applicable to the number of participants at the PhUSE conference that you showed earlier on. This is a journal that wants to highlight that the impact factor goes up every single year. That's what they do. But it's not that impressive. So what they do is, in addition, they tilt the axis. So the curve goes up. If you tilt the axis a bit, it goes up even further. All right? That's maybe a possibility for you to impress people even more about the number of participants, but it's actually fudging with the data. That's giving the wrong impression. And they do it also in the very same journal. They do it in the other direction as well. They want to show a decline, so they show the declining curve, and they tilt the axis in the other direction, so that it declines even more. So it's the same trick they apply, but it's actually fudging, and it leads to misinterpretation of what you should be seeing. So let's agree on a goal that we want to achieve as data analysts, programmers, whatever your profession is. And the goal should be we want to communicate the real story, not fudging the facts, right? So not cooking the data, but really talk about what we have in the data and try to reveal that as efficient as possible. And we should not be moving towards the marketing graph that Stephen Sen in his Devil's Drug Development Dictionary defines as a marketing is a pictorial representation that uses 3 dimensions, 4 colors, and 5 cartoons to show one fact that probably is not true. So we agree we don't want that, okay? One of the principles is that we should maximize the data to ink ratio. Edward Tufte is one of the big guys in the field of visualization. That's one of the slogans that he has put out. Try to use as much of the information in the data and don't use too much ink per data point. And a pretty bad example is what you see on the right-hand side, the all too popular bar plot. This bar plot basically displays 4 numbers, and it uses about 1,000 pixels to display 4 numbers. That's pretty inefficient, really. Actually, the only information it carries is the height of the bar of this category is here, the height of this bar is here, this is here, and this is here. So you could use a single pixel for this data point here, a single pixel for that one, and a single pixel for the other two, and you could get away with 4 pixels and have exactly the same information here. Another point is we want to follow a clear purpose. So the graph actually has a purpose. It's not just there for the sake of having a graph. It has a purpose. You want to show something. And also want to encourage and facilitate visual comparison. What we always do implicitly is you want to compare different treatment groups, different types of co-medications, different types of demographics. So comparing things means the graph has to allow us to compare that. And I'll get back to that with a couple of examples a little bit later on. Should be using few plot types only, such that we don't confuse the reader of these graphs. And helps interpretation. If you really want to read off the values, you can help it by using faint lines in the background so that you can easily read off the values behind particular graphs. And color really should only be used if it somehow supports the analytical process. In marketing, they often use colors and shading and the like to make the graph look fancy, such that even if there's not really much information behind it, it looks good. Oh, well, okay. And to summarize this, what's easy for the human brain is that if we have a common scale, we can easily judge if the one graph is to the left, to the right, above or below of the other. We can judge if the one line is longer or shorter than the other. That's relatively straightforward for the human brain. What's more difficult is to compare angles and slopes. And the prime example is pie charts. If you compare like 2 elements of a pie chart, you have to judge whether the one angle is bigger than the other or smaller than the other, or the area is bigger than the other. So that's quite difficult for the human brain, and there's a couple of examples in literature that show you that pie charts in particular get misinterpreted because it's not easy for the human brain to discern that. And it gets even worse if you move into 3D. There's examples of that later on as well. And colors and shading and saturation should be used if it helps the interpretation, if it contains information. And for that, we will also see examples later on. So, simple example to start out with is we have a table of a couple of values. We look at adverse events. Some people develop a headache in our treatment, others diarrhea, pain, nausea, vomiting, fever, or rash. And we have some cases observed on active treatment, some on placebo, and we have a relative difference between active and placebo. That's one way of putting it. That's a table. Another way of displaying the same information is we put them into a graph. We have the frequency in percent. We have the different AEs. And we have an order. We have rearranged this here such that it's sorted by the absolute difference between active and placebo. This way you can easily see A is active and P is placebo, obviously. So it's not just circles and triangles, it's letters. And that makes it clear that this is active, this is placebo. You can easily tell that the A is to the left-hand side of the P in pain. So that you have more events in placebo than on active in pain. And here's the other way around. At the other extreme, headaches, active is much more common with respect to headache than placebo. So that gives the same information, but it's much easier to discern different information types, such as where is the biggest difference between active and placebo? Do we see a swapping? Do we see adverse events that occur more frequently in placebo than on active, and those kinds of things? And depending on what one is interested in, one can sort the adverse events in different ways. Okay, some of the consequences of the principles I introduced beforehand is that we should aggregate only if really necessary. If there's little data available, it should be shown in its entirety if possible. Aggregation can lead to misleading of interpretation. For example, if we use histograms, depending on how we choose the different categories, you get to see different histograms. That might already be different interpretation. And aggregation, if needs to be, okay, sometimes it does make sense. If you have 10,000 dots, it has to be aggregated in one way or another because otherwise you don't see anything. But the point is, one needs to think about what one does here. And it's very difficult to just automate processing graphics, creating graphics, without thinking about what's going on here and what kind of data we have available. Graphics elements, that's also interesting, in particular for the software developers among us. The focus is always on the data. The focus is on the interpretation. And that implies that the axes, for example, should be kept outside the graphs. As far away as possible, axes are only necessary once to look at the range, for example, and the particular values, but otherwise keep them outside the graphs. Same goes for tick marks, labels, everything that's not really related to data, to the key element we're looking at. Same goes for legend. Legend should not really be inside the graph because that basically takes up the space that could be used for the data. Annotation if necessary, otherwise keep it outside, put it into the legend. Color if it helps, otherwise possibly not. And actually there's a lot of experiments out there that show that the interpretation of graphs is more correct if the data is in black and white or in grayscale. Colors actually distract and lead to misinterpretation. So the point is the graph, the reading of the graph should be intuitive, or in other words, think before you graph. So here's an example for the comparison. This is PK data. We have a couple of patients where we have blood samples over time. This is the concentration axis, and this is the time axis, and all those curves are overlaid. And here, this graph, where the curves are all overlaid in a single plot, allows us to judge, for example, as one graph that has a very high concentration. Concentration occurs roughly at the same point in time, but there's some that have the maximum concentration later on. So that's to get the overall impression of the data. And you see that you have this faint gray lines in the background, which doesn't mean that you can easily read off the value. Like this value, for example, might be 0.032, something like that. If there's no gray line, it's more difficult to move over to the left. If you're more interested in individual profiles, then of course one can also show these. Here you see this guy at a double peak, for example, that one as well. So that shows the individual curves and leads to judgment about particular unusual profiles, for example. So again, the question is, what do we want to look at in these data? Same case again. Now we stratify by body weight. On the left-hand side, you see these are the concentration data of the guys with a low body weight. That's the guys with a medium or average body weight. That's the high body weights. And these are the profiles here, here, and here. And this is the same graph, but the data are arranged differently. So instead of having 3 panels from left to right, we have 3 panels from top to bottom. And the difference is that here you can easily judge on the left-hand side that these concentrations are much higher than the ones here, and these are about the same height, so there's not much of a difference between these two groups here. If you have the same graph arranged in this order, you cannot easily do this. There you really are forced to read off the values. This is roughly where this group is, this is where this group is. It's much more difficult to compare these profiles just because they're arranged in different ways. So this is the bottom line here. Okay. Similar example, we looked at a compound where we had an intervention while the patients were on treatment. We had 4 dose groups, 100, 200, 400, 800 milligrams, and we had the exposure to the drug before the intervention and after the intervention. The dots show the medians, the boxes show the 50% range in the middle, around the median, and the exercise could be, for example, to see not only that the exposure obviously goes up with higher doses, which is kind of logical or expected at least, pre and post intervention, but the question could also be, is there a difference before and after the intervention between the 800 milligrams here and here, pre and post intervention, the same here for 200 milligrams left and right. And for this graph, it's more or less impossible. You really have to read off the values and see there's a difference. If you arrange the graph differently, same graph, same 8 boxes, just arranged in a different way. Now we don't stratify by pre and post intervention, but we stratify by dose group and stack the 2 boxes you want to compare on top of one another. And it's that easy. You see right away, all those medians post-intervention are to the right of pre-intervention, so the interpretation is very obvious, very clear, very intuitive, and the boxes also move to the right. So same graph, just a different arrangement, and that really allows you to interpret these graphs much, much better and much more accurate. Talking about some of the elements that go into graphics, I'm going to sketch now some aspects about axes, lines, symbols, colors, and legends. And after I go through the principles, I'm going to show some examples, some applications of these. Axis range is a very popular topic. This is a graph where we show our compound that might have say, an efficacy of 21.2%, and the competitor might have 21%. But you only realize that this difference is pretty small, from 21 to 21.2, if you read off the values. You can make the values small on the axis, that you don't see them anymore, and you can fudge about with the axis. Now you make the y-axis go from 20.98, so from roughly here, to 21.18. Same data, and now we are the giant, and the competitor is the dwarf down here. All right? So that's one way of showing these data, that leads to very different interpretation. And if you make the axis start at 0, and you go to 25, there's no difference. So choosing the axis, looking at the values at the axis, is actually very important. Another example that's interesting in the world that I live in, modelers and also the statisticians' world, choice of the axis. If you model something, you model a variable as a function of another variable. So you might, for example, want to model how body weight develops with age. Body weight tends to go up. So that means, as a modeler, you put the independent variable on the y-axis, the body weight, as a function of the age. So here's the kind of general trend. As you get older, your body weight increases, at least for most of us. And other examples would be heart rate as a function of the body weight, or body weight as a function of gender and age, but it's not the other way around. It's not that you age because your body weight increases, right? So for a statistician and for a modeler, that means the dependent variable goes on the y-axis and the independent goes on the x-axis, and the regression line shows just that. Point symbols, another consequence of what I said beforehand. Point symbols, open circles are now the choice because open circles are easier to discern. If you use filled circles, for example, it's difficult to see the individual data. If some of them overlay, it's difficult to tell whether it's 1 or 2 or 3 or 4 observations in this very corner. This open circles, you can still tell. This is like 2 or 3 circles that overlay, but they intersect, and you can tell how many there are roughly. Single pixels are too small unless you use big pixels. And circles, triangles, and other symbols are really popular in my environment and in clinical pharmacology, but that means they require a legend. If you, say, code those groups by means of circles, triangles, and squares, and whatever you might have, it needs a legend. It's not very intuitive, and you're always switching back and forth between the legend and the graph, which makes the interpretation or reading much more cumbersome. So one could try different things. One could, for example, use color or some sort of monotonicity. For example, one could use colors from light to dark, which means light is a light dose and dark is a high dose, something like that. That means the darker the color, the higher the dose. One could use edges, lines, triangles, squares, pentagons, those kinds of things to show increasing doses. And that means one has to look at the legend only once, then one understands what's behind it, and then you can really focus on the graph and interpret what's inside the graph. And symbols can also be meaningful. For example, instead of using open circles, as I showed beforehand, one can use A for active, L for low dose, and H for high dose if you have 3 groups. That's much more intuitive. You read this once, then you know what's what. You never look at the legend again. Or also one could use numbers. If you have doses, one could use 1 number or 2 numbers, even if it's not too much data. You can actually put 0, 20, 50, 80 inside the graph instead of squares and triangles and circles. That makes it easier to read. So going back to this is what we had beforehand. And you might have noticed, but you might not have noticed this graph where I showed these data from the table up here. Active and placebo doesn't have a legend, all right? And that is because it's intuitive. It's clear. P is placebo, A is active. And everything else just flows from the graph. Going to lines. For lines, it's really important to keep in mind that lines suggest an order. If you have time series data like in economics or other disciplines, a line shows a trend over time. You have time on the x-axis, you have something else on the y-axis, like the gross national product or something, and the line shows you how things develop over time. But it's an order. You move from left to right. And for clinical data, for example, if you have race as the covariate you want to look at, if you have blacks, Caucasians, Asians, and Hispanic, you should not use lines to interconnect the 4, because that really leads to irritation, right? But I've seen this. So this is the same graph, the same 4 data points, just arranged in a different way, and the graph looks completely different, and it doesn't make any sense to interconnect those with the lines, because there is no order from left to right. Maybe an alphabetical order, but that's of no use. Legend, as I said beforehand, it should be intuitive. At least you should not be forced to look at legend more than once. If you cannot memorize it, if the square was the 40 milligrams, or if it was the triangle or the circle, then it's pretty bad. So there has to be an intuition that makes it easy to focus on the interpretation of the data. You also see here, actually don't see it here, but there's faint gray lines here that help you if you have lots of AEs to discern whether this is the pain or the fever category. And you can use the sorting order. So there's a couple of things that can go into this graph to make it really intuitive and easy to interpret. Colors is always a good example. Colors, we've seen this in the very beginning. Red typically does not mean good. Red is typically bad. Red means red traffic light, red blood, right? So we should not be using red for something that's good in the clinic, right? So as an example, disease improvement should be green, not red, right? And disease worsening could be red, and unchanged, stable disease could be yellow. That's intuitive, and you look at it once, and you got it. Yes, right. So I have a red dot here. That means watch out, right? Okay, so colors can be used if it makes sense, if it helps really focusing on the data, interpreting the data. And that's an example here. Complete responders, green, partial response, yellow, stable disease, orange, and progressive disease, red. Now some applications. That's something that we received last year. That's one of the ugly examples. So we have hours after dosing on the x-axis. No, this thing doesn't work anymore. And we have concentration on the y-axis. And we have the average concentrations per dose group, all at the same point in time. Confidence intervals overlaid, right? So you see the limits of the confidence boundaries, but you have no idea if this is the boundary of that dot here or that dot here. It's completely unclear. There's other attractive features, such as the 95% confidence intervals goes into negative values. So there's a lot of interesting things here. And this CEO actually wanted us to pay for this. Well, okay. So that's an example for how to not do it. An example, again, from the modeling world, if you compare two things, if you want to compare what's on the x-axis and on the y-axis, for example, if we have a model and we have observed data and we have model predicted data, we plot them against one another to check if the model is any good. And if the model is somewhat useful, then those points should scatter around the line of identity. Because that basically means that you get, on average, the predictions roughly to where the data are. And here we have two such graphs. We have predicted versus observed on the left-hand side and on the right-hand side. And if you look at these two graphs and you face the question, what's the better fit, you would think that these points are much closer to this line of identity than these points over here. But actually what I did from left to right is only I swapped the axis. Here it is observed and here it is predicted. Here's the other way around, predicted and observed. And the problem is that this axis is about twice as wide as this axis. So we stretch in the other direction, and depending on how you choose x and y, it looks completely different. And that means that we have to do something about this, and that means basically we have to keep the units fixed. 1 unit on the x-axis should correspond to 1 unit on the y-axis. So if this is like, I don't know, an inch or something between 20 and 30, it should also be an inch on the y-axis between 20 and 30. Otherwise, something is not good. And as a consequence as well, it means that graphs where you compare x and y should be square. It's much easier to see. And then the diagonal, the line of identity, actually goes from the lower left to the top right corner, which just makes sense. I have said this beforehand. This is comparison by ordering. This is different impressions of same data depending on what one is interested in. This is sorted by the occurrence of the AE in the active treatment. So you see the A moves from the left to the right as you move up the y-axis. Here is sort of the absolute difference. Depending on what the question is, the order can be a factor that one can play with to make it easier to see what information we have in the data. We can make it more complicated if the data is more complex. We can play with it. We can use different categories for the different adverse events. Then you can actually plot like 50 or 60 adverse events, group them here, and you can still read them off easily and see what kind of patterns we have, depending on the different AE categories. Another example is change from baseline. That's a clinical endpoint that we often look at. For the change from baseline, a simple graph, a naive graph might be something like this. Here's active, here's placebo, change from baseline over time, starts at 0 and goes in all sorts of different directions. If we polish up this graph just a little bit, what we do is we make the y-axis symmetric, so it goes from -30 to +30, and we put a big black line in the middle. That's the line of no change. And here, it's very easy to see that the change is typically in the positive direction. So almost all the lines go up from 0, and here there's fewer lines going up, there's more down here below 0, and that basically means we do not really have to look at this y-axis and what the values are. It's dead easy to see how many of the lines are above this black line, how many are below. That is more intuitive to read it off that way. And also, if you're interested in particular points in time, when the data was sampled, for example, you can add those gray lines here, then it's quite easy to see, aha, this one is roughly 2 hours, and this one is about, 12 hours. Oops. Now, one of my all-time favorites, 3D. This is a data set that I produced actually while I worked at this very company here some 10 years ago. I still use it. These are 4 numbers again, a lot of pixels for 4 numbers, and the exercise is, what are the values that we see here? You see a y-axis, you see 4 bars, and you see this bar on the left-hand side, for example, goes up to here, here's the line of 10, so that's below that line is just below 20, and that line is below 30, that line is below 40. But the question is, what's the value? And the answer is, this is 3D. The most important part of this graph is this gap between the bar and the rear wall. All right, you're looking at the bar from the bottom. So what you have to do is you have to take this bar, grab it with your hands, shove it up the slope, and then against the rear wall, and the value of this bar is actually 10. Yeah? And I only noticed this because these 4 values at the time had to sum up to 100, and they didn't, according to my reading. So that's an example how you can be misled, and you can be fooled into this kind of thing in 3D. People take it even farther. This is a 3D with several categories behind one another. What you see here is I just rotated the values, the same 4 values as before, 10, 20, 30, 40. So these 4 bars represent the same value. You wouldn't think that. It's only because they are on a slope, all right? So that leads to misinterpretation. And you see that the 2D graph of the same data is much more accurate. Here you see exactly that these are the same heights. So 3D can lead to very serious misinterpretations. But the good news is, using this well-known spreadsheet type of approach, the first option that you have in the spreadsheet is you can show the data table. That means the graph is useless. Why don't we put the data onto it? Right? That's my interpretation of it. Because you cannot really do something with this graph on maybe only admiring it because it looks so great. But if you want to interpret it, you have to see the numbers, and that's what they do. Same goes for the pie chart, same situation. This pie here is a value of 10. This is a value of 10. That's the value of 20. But what you see is this one is in front, so you see a lot of red here because you also see the side. And for this pink bar in the back, you see about the same number of pixels, maybe even fewer pixels than for this part of the pie. And that means it's very difficult to interpret this. But again, the good news is again that for this example, you can also put the data inside this pie chart and then you are back on track. Well, okay. Higher dimensions. Another example that can actually be something useful. This is a visualization of the FEV1. That is the amount of air that you can exhale in 1 second into a device that measures how much volume it is, how many liters it is. And this is a function of the body weight that you have and the age that you have. And the bad news is that as you age, you're able to exhale less amount of air per second. And as your body weight increases, of course, you have bigger lungs, so that means the volume you can exhale goes up. So that's the kind of general tendency here that you see in the surface graph. But reading off the values doesn't really make any sense. So basically it's color-coded, but there's no axis here because it's kind of useless. And if one is really interested in the values, we can use the slices. So what I did is I used this line and 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 stacked it up down here. And then in the other direction, slicing the 3D surface using this line and that line, stack them here. And here you can read off the values if you're interested in particular values. So some more examples, going through this quickly. This is one of the world famous examples for visualization. It was created by Edward Tufte some 20 years ago, no, not 10 years ago. This is a big study that was published in The Lancet, one of the prime medical journals, on the survival rate for patients having different types of cancer. You see the cancer sites on the left-hand side, and you see the survival rate after 5, 10, 15, 20 years, and the standard error in brackets after it. That was published. It would create quite some stir. And then one of the big guys in the field of visualization, Edward Tufte, went ahead and said to himself, how can I visualize this better? There's a lot of information, there's lots of interesting information, but I want to visualize this much better than this. What he did was, first of all, he sorted the data. So the people with the highest chance of surviving after 5 years come first, which tells you prostate cancer has a good survival rate, pancreas has a bad survival rate for 5 years, and he made the average survival rates bigger than the standard errors because they're less interesting. That's already the first step towards the better interpretation of these long-term survival data. And then second, he went ahead and made this kind of semi-graph table. Here, he used the prostate and showed 5, 10, 15, 20 years on the time axis and how it developed. So you see prostate survival rates, they're relatively stable over 5 years. There's some drop from 99 to 81% after 20 years. And this type here, the thyroid also stays relatively stable. Others are pretty bad. If it's larynx cancer, you still have quite a high risk of not surviving 10 years if you have survived 5 years, so this trend is still downwards. This is a very nice visualization that has become really famous. Actually, if people search for survival rates in cancer, they largely end up on this site now because that has the biggest number of hits before all medical journals. So that's a very nice example for a combination of graph and table. And it took some artistic freedom actually, because what you do see is that it's not exactly to scale, that some of the lines should be intersecting, but they don't. Like this guy, for example, the multiple myeloma moves from 30 to 13%. So it should intersect with the stomach cancer, but it does not for artistic freedom because you see the profiles better if you do it that way. Another example here. This is a biomarker that I was asked to look at a couple of years ago. We have the concentration of the biomarker on the y-axis. We have the time in days on the x-axis. So it's half a year study. And there's a lot of data inside this graph that we handed back to the principal investigator at the time. So that's the concentration of the biomarker over time. The color code is the clinical response. Green is good response. Yellow is stable disease, and red is progressive disease. So what you see here is that as the biomarker increases for these patients, the curve becomes green, and that means you have a clinical response. Then the biomarker goes down over time, and the curve turns red, so that means we see a clinical worsening for this patient. That's all inside this graph. And on top of that, we added the normal ranges, the horizontal lines here. So this is above the normal range, below the normal range, and this is the dose history. So here you can see the guy was on 40 milligrams for a while, then there was no drug given for maybe a month or so, then back to 40 milligrams, dose was halved, so there's something going on in the background behind this. And all this information is in a single and relatively simple plot, actually. So that's to say that basically graphing clinical data can actually be an art, and it really helps the clinicians understand the data, understand the raw data. There's no processing, there's no statistics behind it, it's the raw data. And the clinical people really appreciate this because they understand what's inside the data. And we can actually do this for more than 1 or 2 patients. You can do this for 12 or more, so that is still legible. Okay. Another way of looking at values that are typically studied by numbers is from the modeling world, big correlation matrix of parameters that are correlated, and you get a big fat table of numbers, which is very difficult to look at because you have to study all the numbers. The idea would be to color code these. So you have a correlation going from -1 to +1. +1 is dark blue, -1 is dark red. And you see that, for example, this block here, these parameters have a pretty strong correlation. This block down here shows the same thing. Of course, in the diagonal, it's all 1. And the red have a strong negative correlation. So this parameter here correlates strongly negatively with these up here. That's very easy to see, not studying the numbers, but just using color codes to show a, 15 by 15 matrix. Another example from my world, this is the drug concentration. steady state concentration if you want. That's the clinical response. And this is I think it's an Emacs model. Yeah, right. And here what we do is we show the individual points that we have observed to our concentration, clinical response, and you see with higher concentrations, clinical response goes up, the model stays the same, curve goes up, confidence intervals here. And on top of that, we have 3 different dose groups. We have given 50, 100, and 200 milligrams. That's the 50 milligram group, 100 milligram group, 200 milligram group. And down here, you see the distributions. So this is the typical concentration for the 50 milligram group down here. This is for 100 milligrams, that's for 200 milligrams. And again, since we indicate the medians of the dose groups by those color symbols, it's quite clear that the triangle here, a 200 milligram group, is the group up here. It does not require legend, it's intuitive. Okay, and the ultimate sophistication is the children's pool. What will you imagine to be in the children's pool? Very intuitive reduction to just the very basics of the graph. There's 2 elements in the pool. There's the water and there's the yellow part. No legend required, it's intuitive, right? Okay, moving to the summary. 1 minute left, so that'll be spot on. Graphical presentations of PK data, AE data, lab data, vital signs data can provide clear messages. It can also provide very unclear messages to the extent that it confuses people, but it can actually help the interpretation a great deal. It anchors the clinical study report. If you browse through a report, if you browse through a book, what you get stuck at are the graphics typically, or the tables at times. So that's really an eye catcher that really anchors the report. That's what people look at. And one has to be able to rapidly and accurately identify the information. The key roles for graphics are exploratory graphics, review graphics, submission documents, and presentations, such as this one. And a glimpse of the future might be, I put a question mark here because I'm not convinced myself yet, is standardization of data formats and graphics. Because largely, pharmaceutical companies tend to have libraries of what kind of tables they produce, and they try to do the same for graphics, but that's a bit more difficult because, as I argued beforehand, one has to think about what one wants to show, what's inside the data. So one could imagine that based on the SDTM format, data gets standardized across the industry. And actually there is, jump to this first, there is an initiative underway. It's ctspedia.org, clinical trial something, pedia.org, that provides a library of safety graphics and code, actually codes from all sorts of languages, from SAS to R and whatever you might be interested in. And other things about reading on visualization. This is a beautiful book by Edward Tufte, Envisioning Information. Another one is called Beautiful Evidence. These are the types of books where we really talk about data, how to visualize data, what kind of principles and concepts you should be following. Another one I read last year is Mr. Beck's Underground Map. That's a lovely book to read. This is about the development of the Tube map in London, the Underground map, right? They have really spent days and days and days and years on developing this map, to the extent that a couple of years ago they took the Thames River off the map because they said it doesn't provide any information to it. There was a big uproar in the press and they had to put it back on. But it's a very interesting and nice book about visualization. Another one is the design of everyday things. That's one way of how you should not design a teapot. That talks about designing of the daily appliances, basically. Then Phil Lowe and I have put out a book on visualization and communication of an article on visualization and communication of PKPD models. And about a year ago came out this book. That's also in the video that we have seen. The pictures worth 1,000 tables, graphics and life sciences. I talked to the publisher, and actually you can get your voucher of 20% discount. So sorry for this little advertisement, but for this very conference, it's a 20% discount. Okay, that's it. This is an acknowledgement of my co-workers, Michael O'Connell, my co-editor on this very book, the other authors, some in the audience actually, such as Michael Mertz, providing chapters to this book, Graphics and Life Sciences, many colleagues at different companies for many good discussions on graphics, and also for thank you to those anonymous donors for providing examples, the good examples, the bad examples, and also the ugly examples, because you can learn from all of them. Thank you very much.